So this little video is going to focus on molarity review, dilutions, pH, pOH. Basically, we're going to look at summer homework questions 20 through 23 because these are all related to those topics. So I've added here to our screen the formula that you're given on the 10th grade reference materials. So molarity is moles of solute, the stuff that's being dissolved, divided by the liters of all the solution. And then here we have our formula for making dilutions, volume times molarity, volume times molarity. And then here we have the formula for pH. Again, this is all on the 10th grade reference materials. For IB, we are given pH, and that's it, which means that these two guys you need to have memorized. Definitely have these two formulae memorized. Molarity is moles over liters. Volume 1, molarity 1 equals volume 2, molarity 2. So question number 20, a solution is made by dissolving 17 grams of lithium iodide in enough water to make 387 milliliters of solution. What is the molarity of that solution? So we definitely need to use this first formula, molarity, because we're trying to find molarity. So I need moles of solute, and nowhere in my question do I have moles. And then I need liters, and I also don't have liters. So we're going to have to do some converting before we can apply this fairly simple formula. Lots of steps before we can get to that. So let's start here. We have 17 grams of lithium iodide. I need to turn that into moles of lithium iodide so I can plug it into the formula. So in order to turn grams into moles, I need to find the molar mass. And so I go to my periodic table and I see that lithium and iodine have these two masses. But I need to go back to my name and make sure that my formula, this is ionic, since it's metal, non-metal, has balanced charges. So handy dandy periodic table, lithium is in column number 1. It is an alkali metal, which means it's going to have a charge of +1. And then iodine is a halogen, column number 17, which means it's going to have a charge of -1. Quite happily, those two balance each other out. +1 minus 1 equals a 0. This is always our goal for ionic compounds. So our formula for lithium iodide is simply LiI, which is nice. I just have to add those two guys together. And the molar mass of lithium iodide is going to end up being 133.84 grams per mole. Good. So now that I know the molar mass of lithium iodide, I can go back to my 17 grams and turn those grams into moles. I have 17 grams of lithium iodide. I'm going to turn it into moles by putting the mass on the bottom because I want those grams to cancel out, and my 1 mole on top. Remember that the periodic table always tells us how many grams are in 1 mole. Always these numbers, how many grams in 1 mole. My grams on top here, my grams on bottom here cancel out. And so now all I have to do is multiply everything on the top, divide on the bottom. Our little pieces of the railroad track are simply telling us to multiply and divide. So we multiply everything on the top, divide by everything on the bottom. So 17 times 1 divided by 133.84 is going to give us a grand total of 0.127 moles of lithium iodide. This is not our final answer. I now have the mole part. I still need my liter part before I can find molarity. So back to the question, 387 milliliters. We need to turn that into liters. So there are 1,000 milliliters in 1 liter. And so therefore I can either divide this by 1,000 or the very nice shortcut. Oh, the beautiful zeros of the metric system. All we have to do is move our decimal place back equal to the number of zeros that we're dividing by. So 1, 2, 3. And so milliliters will turn into liters by putting our decimal place there. So we're going to divide by 0.387 liters. And now all I have to do is divide moles divided by liters. 0.127 divided by 0.387 is going to give us 0.328 molar. In IB world, we don't use big M for molar. Instead, we do moles times decimeters to the -3, which this is the same thing as dividing by cubic decimeters, and a cubic decimeter is the same thing as a liter. I don't know why we can't just write a big M, considering it means the same thing, but be aware in IB world, we'll see this instead of that. Feeling good so far? Again, if that wasn't enough, if you need more words, more review, let me know. Let's look at question number 21. What volume of 18 molar sulfuric acid, which by the way is crazy scary, melt your face off acid, required to make 16.5 liters of 0.126 molar sulfuric acid? This diluted version, not so scary. So we need to use the dilution formula, which is this one. Again, this is one that you need to memorize. This is not given to you in the IB formula book, so make sure that you memorize this. I learned the reverse order. So I will almost always do M1 V1 equals M2 V2, but just like 2 times 3 equals 3 times 2, they both make 6. V times M is the same thing as M times V. Doesn't even matter. So I am going to do M1 V1 equals M2 V2. In my question, I have an M and I have a V, and I have a V and I have an M. And this is 1 and 1, and this is 2 and 2. So now I just have to plug things into my formula. So 18 molar for M1. V1 we don't know, so I'm going to leave it as V1. Set that equal to M2.126 times, oh, I missed my parentheses, times the volume 16.5 liters. Solve for V1. This is easy algebra. Divide both sides by 18 molar. Cancels out, cancels out. Over here, we need to do some calculating. 0.126 times 16.5 divided by 18 gives us 0.116 with our sig figs, 0.116. And let's check our label. So I have molar on top and molar on bottom. Those cancel out. We're left with liters, which is good because we're trying to find volume. And a label of liter is going to tell us what the volume is. So our answer is 0.166 liters. If I wanted to convert that to milliliters, I could multiply by 1,116 milliliters. So what this means is that I'm going to take 116 milliliters of this crazy strong acid, and I'm going to combine it with lots and lots and lots of water until the total volume is that 16.5. So we could do that subtraction 16.5 minus 0.116, whatever that is. It's a lot of water and a little bit of acid. Combine those and we would have that diluted version of the sulfuric acid. All right, let's talk about pH here a little bit. So this is the formula for pH that you're given in the IB data booklet. And we'll talk really quickly about what pH even means, and then we'll look at the problems. So pH is the log base 10 of the hydrogen ion concentration. Acids are always going to be H something. And so we assume that whatever the concentration of the acid is, it's going to be equal to the concentration of the H or the H plus because they're stuck together. We will talk later about some exceptions to that, but for now, we're going to work on the assumption that whatever is the concentration of the acid is also the concentration of the H because the H is stuck to the acid. It's coming with the acid. So whatever the acid is, the H also is. Again, that will not be true later, but for now, we're good. So pH, what we're going to do is take that concentration of the acid. So let's say that we had some hydrochloric acid and it had a concentration of 0.1 molar. To find the pH, I just want to know 10 to what power is equal to that concentration. 10 to what power is equal to 0.1? Well, 10 to the minus 1 power is equal to 0.1. But my pH, and so this is my exponent, my pH is the negative version of that. So I'm going to find the pH is going to be the exponent, but the negative version of the exponent. So negative 1 is a positive 1. If we have hydrochloric acid with a 0.1 molar concentration, the pH of this would be 1. So let's say that we had some other hydrochloric acid and it had a pH, a concentration of maybe 0.00429. So 10 to what power is going to give us 0.00429? I have no idea. I can't do that in my head. And so I have a calculator. Click the log button, plug in 0.00429, log, turn your calculator on. log of 0.00429 is going to give us negative 2.368. But because pH is, again, negative log, I want the negative, or positive 0.2368. So this would be the pH of an acid with that concentration. So far, so good? So far, so good. So let's talk about then. I'm going to erase a little bit here so that we have more space on the screen. Let's talk about this idea of pOH. So the pH is the negative log of the concentration of the hydrogen ion that comes from acids. What's kind of crazy is that the opposite of that hydrogen ion, oh dear, what did I do? Sorry. The opposite of that hydrogen ion concentration is the hydroxide concentration. Because what's crazy is that if I mix this guy and this guy, we end up with water. So they kind of cancel each other out. So we talk about pH and pOH. This is based on the hydrogen ion concentration. This is based on the hydroxide ion concentration. And when I combine those two, we make water and things cancel out. We have a pH of 7. And so what's kind of crazy is that if I add the pH to the pOH of any solution, I get 14 because the pH of water is 7, which means that the hydroxide concentration in water, these guys are the same, is also 7, and so 7 plus 7 is 14. But if I don't have water, we can throw any old numbers in there. So if I'm looking at this guy, a pH of 3.70, plus the pOH is going to give us 14, so I can subtract 3.7 from both sides, which is going to give us a pOH of 10.3. So the pOH is 10.3. How did we get that? Well, we had some hydroxide concentration, and I took the negative log of it, and the negative log of the hydrogen ion concentration, and that gave us 10.3. Remember that logs are the exponents on a 10. Since it's common log, we don't have a base given, common log 10. So what this means is that when I figured out what the exponent was on the 10, it was this. So to go backwards, all I have to do is put my pOH as an exponent on the 10. So that the hydroxide ion concentration is going to be 10 to the pOH, except, my friends, the formula gives us a negative, so we're going to have to make it 10 to the negative 10.3. So when I find the pOH or I find the pH, I'm finding the log. If I want to go backwards, I have to put the log, the exponent, back on the 10, our base 10. So handed in a calculator, 10 to the negative 10.3 power is going to give us a hydroxide ion concentration of 5.011 times 10 to the negative 11 molar. Good-ish? Yeah? Maybe? This one might be a little fuzzy. This is hard stuff. So again, if you need more, let me know. We're going to do number 23. This is actually easier because I don't have to find the hydroxide piece. We just need to find the hydrogen piece. So again, pH is the negative log base 10 of the hydrogen ion concentration, which means that I'm trying to figure out 10 to some power, which happens to be the pH, is going to be equal to that hydrogen ion concentration. So hydrogen ion concentration is 10 to some power. We give that power the value of pH. Throw the negative in there. Don't forget the negative. So if I have the pH of 4.37, that means that 4.37 is the negative log base 10 of the hydrogen ion concentration. So the hydrogen ion concentration is going to be equal to 10 to the negative pH, 10 to the negative 4.37. Whoa, that was a weird 7 is going to give us the hydrogen ion concentration. Thank goodness we have calculators. I wouldn't even know how to do that on without a calculator. So 10 to the negative 4.37 power is going to give us a value of 4.2, 4.27 when we round, times 10 to the minus 5 power. Don't lose that scientific notation. Big M for molar. So this would be the concentration of the hydrogen ion in the pH acid 4.37. Ish, good, maybe, good, okay. That's all I've got for these couple questions. Again, if there's anything that you need more details about, let me know.